Welcome dear learners. We are continuing Unit 5 Inorganic Chemistry Practical 1 Volumetric Analysis. In the present module, we are discussing estimation of iodine. The contents of this module are iodimetry and iodometry, aim of the present experiment, principle behind the experiment, reagents required for the experiment, experimental procedure, that means preparation of standard K2Cr2O7 solution, standardization of sodium thiosulfate solution and estimation of iodine. Finally, results of these analysis. First of all, iodimetry and iodometry. You are very much familiar with the volumetric analysis. This is an analytical procedure where we are measuring the volume of one analyte. By comparing it with the volume of a standard solution, it is possible to estimate the analyte. In iodometry and iodimetry, we are using iodine as a reagent to perform the volumetric analysis. We can now enter into the details of this iodimetry and iodometry. The volumetric analysis based on the use of iodine as oxidizing agent is called iodimetry or iodometry. Iodimetry deals with the direct titration involving iodine solution. However, iodometry deals with the titration of iodine liberated in chemical reactions. Hope this difference is very much clear to you. It is very important as far as the titrations with iodine are concerned. In iodimetry, we are using a solution of iodine directly. However, in the case of iodometry, we are performing titration reactions with the iodine liberated during a particular reaction. Now, aim of the present experiment. The aim of the experiment is to estimate the amount of iodine in the whole of the given solution. And for this experiment, approximately n by 10 sodium thiosulfate solution and annular potassium dichromate crystals or K2Cr2O7 crystals being supplied with. So, you have to estimate the amount of the given iodine solution or iodine present in the given solution by the utilization of these two important reagents. They are nothing but n by 10 sodium thiosulfate and annular potassium dichromate crystals. Now, the principle behind this experiment. Annular potassium dichromate crystals is used to prepare a standard solution with which sodium thiosulfate can be standardized. This is very important. You know the fact that potassium dichromate is a primary standard. We can take a fixed quantity of the potassium dichromate crystals, weigh out it accurately, and can be prepared for and can be used to prepare a standard solution of potassium dichromate. That standard solution can be titrated with the sodium thiosulfate, which enable the standardization of the given sodium thiosulfate solution. Now, in the presence of hydrochloric acid, potassium dichromate liberates iodine from a solution of potassium iodide. The reaction responsible for this liberation of iodine from potassium dichromate, iodine from potassium iodide by potassium dichromate is like this. K2Cr2O7 plus 6Ki plus 14 HCl produces 2 CrCl3 plus 8 KCl plus 7 H2 plus 3 molecules of iodine. From this equation, it is clear that in the left hand side, you can see potassium dichromate which contain chromium in plus 6 oxidation state. It is just converted to CrCl3. In a CrCl3 molecule, chromium is present in plus 3 oxidation state. So, there is a decrease in oxidation state of Cr plus 6 to Cr plus 3. That is, potassium dichromate as such acts as an oxidizing agent in this reaction. At the same time, the oxidation state of I minus present in potassium iodide is converted to 0. That is, I minus undergo oxidation to produce iodine. So, it is very well clear that this is a redox reaction. So, in this reaction, iodine is liberated. Now, in this reaction, the equivalent mass of potassium dichromate is calculated as the equivalent mass of an oxidizing agent is equal to molar mass divided by change in oxidation number, Based on that argument, we will get the value of potassium dichromate as 49. Now, the liberated iodine in the above reaction is titrated with the sodium thiosulfate solution. Iodine oxidizes sodium thiosulfate solution or sodium thiosulfate to sodium tetrathionate. This is the reaction responsible for the oxidation of sodium thiosulfate to sodium tetrathionate. To Na2S2O3 plus I2 gives Na2S4O6 plus 2 molecules of sodium iodide. Since in this reaction, one molecule of Na2S2O3 reacts with one equivalent of iodine, the equivalent mass of Na2S2O3 is same as its molar mass. However, Na2S2O3 is available as Na2S2O3 5H2. Therefore, the molar mass of Na2S2O3 5H2 is same as its equivalent mass, and that is equal to 248.19. Using the standard sodium thiosulfate solution, the given iodine solution can be estimated. That means we first standardize the sodium thiosulfate solution using a standard solution of potassium dichromate. And by utilizing this sodium thiosulfate solution, we can estimate the presence of iodine in the given solution. This is the reaction which is already familiar to you. In this reaction, the equivalent mass of iodine is its atomic mass. The atomic mass of iodine is 126.9, and in this case we can round off to be 127 for the sake of doing calculations. Now, in both the titrations, that is in standardization as well as estimation, we can use starch as the indicator. At the end point, the blue color changes to colorless. Now we can enter into the reagents required for the present experiments. These are the reagents. First one, Ar potassium dichromate crystals. 2, approximately n by 10 or 0.1 normal solution of sodium thiosulfate. Now, iodine solution, that is used for the estimation of iodine. You are provided with an iodine solution, and by using this solution, you have to estimate its iodine content. Now, the fourth reagent is concentrated hydrochloric acid. Next reagent is 5% potassium iodide solution. From the principle, you are familiar with the fact that you have to use potassium iodide, from which iodine is liberated by standard potassium dichromate. Now, starch solution. Starch is used as indicator in both the standardization as well as estimation. Now, we can enter into the procedure of the experiment. The first part of the experiment is preparation of a standard potassium dichromate solution. The mass of potassium dichromate required to prepare 250 ml of n by 10 solution can be calculated by using the popular equation weight required equal to VEN divided by 1000. In this expression, V represents the required volume, E represents the equivalent mass of the primary standard, N represents the normality of the required solution. In the present case, the weight required will be equal to 250 ml volume multiplied with the 49 is the equivalent weight of potassium dichromate into 0.1, that is the required normality, the whole divided by 1000, you will get a weight value of 1.225 gram. Now, roughly weigh out 1.25 gram of Ar potassium dichromate and transferred to a dry weighing bottle. It is then weighed by an electronic balance, and the weight is now recorded as W1. So, W1 represents the weight of the substance plus the weighing bottle. Now, the substance is transferred from the weighing bottle into a 250 ml standard flask through a funnel and made up to the mark. Now, the weight of the empty weighing bottle is recorded as W2. Therefore, the actual weight of potassium dichromate is given by this equation W1 minus W2. Remember, W1 represents the weight of the weighing bottle and the potassium dichromate. W2 represent the empty weight of the weighing bottle. So, the difference gives the actual weight of K2Cr2O7. Now, this weight W1 minus W2 is used to find out the concentration of potassium dichromate solution as normality of the resultant solution will be equal to weight per liter divided by equivalent weight. Now, for the titration, or for the volumetric analysis, we are using conventional titration procedure apart from the double burette method of titration. For this, for performing the standardization of sodium thiosulfate solution, 20 ml of the made up potassium dichromate solution is pipetted out into a clean conical flask and add 3 ml of pure concentrated hydrochloric acid. About 10 ml of 5% potassium iodide solution is added. Diluted the solution to 100 ml and titrated against sodium thiosulfate solution taken in the burette. Now, the addition of sodium thiosulfate is continued until the solution is pale yellow in color. About 2 ml of starch solution is added now and the titration is continued until the blue color changes to green. Repeat the titration for concordant values. In volumetric analysis, concordant value refers the value, means in 2 consecutive titrations you have to get the same value. Such a value is considered as the concordant value of the titration. Now, standardization of sodium thiosulfate demonstration. We are now entering into the lab and going to demonstrate the first part of the experiment, that is nothing but standardization of sodium thiosulfate. we have conducted the standardization part experimentally, and now we are going to perform the calculation, that is standardization of sodium thiosulfate solution and calculations based on this. The weight of potassium dichromate taken is already recorded as W1 minus W2 and it is equal to 1.265 in the present experiment. Weight of K2Cr2O7 per liter is obtained by multiplying this quantity with the 4, since you are transferring this 1.265 gram of potassium dichromate to 250 ml. So, the weight per liter, weight per 1000 ml is obtained by multiplying this quantity with the 4 and you will get a value of 5.06. Now, the normality of potassium dichromate solution is equal to weight per liter divided by equivalent weight. That is 5.06 divided by equivalent weight 49, that is equal to 0.1033 normal. This is the normality of the standard potassium dichromate solution we prepared to standardize the sodium thiosulfate. Now, the titer values in the titration between sodium thiosulfate and standard potassium dichromate can be tabulated as follows. This is the titration against K2Cr2O7 and sodium thiosulfate. So, the volume of potassium dichromate pipetted out will be equal to 20. You will get the concordant value of the titration as 20.4 ml. That is the volume of the solution of sodium thiosulfate performed in this titration is equal to, is taken as 20.4 ml. Now, from the titer value, we can calculate the normality of sodium thiosulfate using the volumetric relation N sodium thiosulfate into V sodium thiosulfate equal to N potassium dichromate into V potassium dichromate. In the present experiment, we already got N potassium dichromate equal to 0.1033 normal. Volume of potassium dichromate is equal to 20 ml. Volume of sodium thiosulfate is equal to 20.4 ml, which is the concordant value of the previous titration. Now, we got the normality of sodium thiosulfate solution as 0.1013 based on this volumetric relation. Now, we are entering into the last part of the experiment, that is estimation of iodine. The given iodine solution is made up to 100 ml in a standard flask and 20 ml is pipetted out into a clean conical flask. The solution is titrated against standardized sodium thiosulfate solution until the color of the solution becomes pale yellow. Now, the solution is diluted to 100 ml with distilled water. At this point, 2 ml of starch solution is added as the indicator. The titration is continued until the color changes from blue to colorless. Repeat the titration for concordant values. Here also you have to get the concordant value in the titration between the given iodine solution and sodium, standardized sodium thiosulfate. Now, we can estimate the iodine, and now we are entering into the laboratory procedure behind the estimation of iodine, that is demonstration of estimation. conducted the experiment and now entering into the calculation part associated with estimation of iodine. The titer value in the estimation can be tabulated as follows. Iodine solution against sodium thiosulfate is the last titration and the concordant value of the titration is obtained as 20.1. That is, volume of sodium thiosulfate used against the given iodine solution is 20.1. The volume of iodine solution pipetted out is seen in the second column of this chart. That is, volume of the solution pipetted out is equal to 20 ml. So, we got the concordant value, that is the volume of the sodium thiosulfate solution is equal to 20.1. Now, we are doing further calculations based on this titer value. From the titer value, we can calculate the normality of the iodine solution using the volumetric relation. N1 V1 is equal to N2 V2. In this equation, it is clear that N1 represents normality of the iodine solution. V1 represents volume of iodine solution. N2 stands for the normality of sodium thiosulfate that we already standardized and we got the value equal to 0.1013 normal. And V2 stands for the volume of sodium thiosulfate solution, that is the concordant value in the last titration, which is equal to 20.1. So, N1 will be equal to N2 V2 divided by V1. On substituting the proper values, we get the normality of the iodine solution is equal to 0.1018 normal. So, we calculated the normality of the iodine solution. Now, the weight per liter of the iodine solution can be calculated from this normality. This is by utilizing the expression weight per liter is equal to normality into equivalent weight. Normality is calculated as 0.108 normal, just to multiply with the equivalent mass of iodine, that is equal to 126.9. We will get a weight per liter value equal to 12.92 gram per liter. So, we got the weight per liter of the iodine solution. Now, mass of iodine in the whole of the given solution can be calculated by using the expression weight per liter divided by 10. By 10 comes from the fact that you made up the given solution into 100 ml. So, 100 into 10 will get the weight per liter. So, you have to divide weight per liter by 10 to get the amount of iodine present in the 100 ml of the solution or in the whole of the given solution. So, weight per liter is equal to 12.92 divided by 10, that is equal to 1.292 gram. So, we got mass of iodine in the whole of the given solution as 1.292 gram. Now, the final result of the experiment. The normality of the given iodine solution is equal to 0.1018 normal. Now, weight per liter of iodine in the solution is equal to 12.92 gram per liter, and finally, the mass of iodine in the whole of the given solution is equal to 1.292 gram. Thus, in the present experiment, we have demonstrated the estimation of iodine provided with the potassium dichromate crystals and sodium thiosulfate solution. That all about the present module. Have a nice learning experience. Thank you.